World is going crazy over Tony Ferguson training with David Goggins.
This is where you win. This is where you win right here. Come on, Tony. This is where you win.
David Goggins started training Tony Ferguson in a brutal Hell Week camp. David said in a recent post that Tony finished Hell Week today. I have had many people try, yet he is the first one to get through it. I have had a lot of great athletes over the years want to train with me, but for one reason or another, something always miraculously comes up so they can't complete it. There is a look I see on the faces of people who are on the brink of quitting called the 1,000-yard stare. They start asking questions: when is it going to end? What's next? How many sets are left? Are we coming back again tonight? Is this healthy for you? This is when I usually start laughing my ass off. I tell them it is time to pack your bag and go home. Once you start asking these questions, I know you are not committed. I broke El Kukui on day one, or at least I thought I did. I had him deep in the hurt locker and figured the questions were soon to be coming. I told Kish late that night, this motherfucker is done. But, I was wrong. He woke up on day two even more fired up to go. There was never a question asked. His response was always the same: okay, coach. Around 11 p.m. on Wednesday night, when he could barely walk after having completed nearly 2 miles of walking lunges and a shit ton of other.
Hello?
Hello, Chris. Hi, how are you?
Right now I'm a bit sick.
Oh,
Okay.
so just flu or COVID?
I don't know. It might be just a cold, I think.
Okay, hopefully, right?
Yeah.
Yeah, well, it's difficult to say. So, okay, quite tired? Headache?
A bit, I guess.
Uh, Probably, yeah. So, okay, so yeah, let's see, huh? That you can still be here despite the headache. That's usually quite a hindrance.
Yeah.
But okay. We start with a new chapter today because we really covered everything in the density part. So I would start today with electricity. Is that okay?
Yeah.
All right. So let me just share screen. All right. So you empty page, huh? You see that, Chris? So we are connected, huh?
Yeah.
All right. Okay. So in the book they start with all the circuit symbols, but we leave that aside because we are not going to discuss circuits yet. So all these symbols for the various components of an electrical circuit, we discuss that, so say maybe next time when we really start with the circuits, because first we have to cover quite some ground about, well, what are the basic principles, phenomena, etc. for, well, what we call electricity, right?
Yeah.
And I like this. What they start with is, I like it. So I would take that up and say, what do you understand when I say electricity? What is your understanding of electricity? What comes to your mind? I mean, it doesn't have to be scientific, doesn't have to be according to the textbook, just what comes to your mind when we say electricity or talk about electricity.
Like charge
Okay.
and energy.
All right. Okay. Yeah. Good. Right. So, I mean, the key point they make in the book, which is a very good remark, is it has a very wide range of meaning, electricity in general terms. So we moving more towards the scientific and becoming scientific. So we use the specific terms in that context. So electricity is like a big umbrella, but we see already in the chapter naming, it's not just called electricity, it's already called electric current, potential difference, resistance, right? So these are just 2 or 3 actually of the very important parts of under the header of electricity. But again, we will not typically use that general term electricity per se. No? So Okay, so that's why we start with the most obvious one, and we talk about electric current. Uh, so when we talk about electric current, we can say typically we have a wire, but first we have to start. This is the only symbol right now we're going to use.
I think you're not sharing screen.
Is it gone again? Ah, okay. All right, thanks. Okay, yeah, it just cancelled itself. All right, okay. So here we go. Okay, so and we just have a wire. It can be free from. Typically in a circuit, of course, we use very rectangular stuff, but of course it can be a wire, so whatever. Huh? And we have a flow of current. So flow of current means, well, when I say flow of current, Chris, what is that really? That flow of that current or that flow of current?
Like the conventional current is the imaginary flow of positive charge.
Okay, all right, okay, good, yeah. So we're talking about electrons, right? So the whole confusion from this conventional current and the flow of the electricity, which are obviously in opposite directions, is just because at the time when the discussion or when the concepts came up and electricity came quite far in the 19th century, so 1830ish until 1880, there was a massive development. But at that time, the concept of protons and electrons was not yet known. So they came quite far without knowing about that. That's quite amazing, actually. And at that time, current was related to the flow of positive. I mean, in the end, it's just in a name, right? You can call it a chair, a table, and vice versa. It's just in the end, what do we agree upon? Then we know what it is. So at that time, the flow of current was considered to be something positive, and hence that's why the conventional current came into existence. Huh? So, and the typical thing you see here as well is that when we do the so-called cell, that could be, I mean, that could be a battery, that could be an electrical cell which is producing the energy at that moment through a chemical reaction, or it could be as well the plug-in in a socket actually. You know? And then we see that the longer one is the plus. So that's very easy to remember. Just the longer of these two is the plus one. Henceforth, of course, when we talk about the flow of the electrons, in which direction will the electrons flow?
From the negative to the positive.
Exactly. Huh? So what is therefore shown in my plus, in my arrow direction?
It's the opposite to the electron flow.
Okay, exactly. Huh? So we call that, and that is, I make it like this. Let's say this is the conventional. Oops, that's not really nice. So this is the conventional flow. Huh? When you go from plus to minus, whereas make it like this. This is the flow of electrons, huh? Or electron flow, because they go away from minus obviously to plus. So when that's why sometimes it's a bit tricky to figure out now what are we talking about, right? But in a typical situation, when the question is what is the in a circuit, the labeling is exactly like that, and the flow of the electricity is then considered as the conventional flow. Only when we go on to the electron level, we have to remember that it's exactly the opposite. I mean, which is kind of logic, of course. The conventional flow is kind of not logic, but it has a historical explanation. Huh? And that confuses the whole thing because under normal circumstances, talking about the circuit, we talk about plus to minus. Very strange. So the red one counts because the pluses go away from the plus at the time when it was considered to be a plus charge. And that's why the labeling is according, this is the plus, and then it's considered that the current flows like that from plus to minus. However, when we talk about the electron flow, of course, it's like this. And that is extremely important when we come to the EMFs, the electromagnetic forces, together with the Lorentz, also the combination of flow of electrons and a magnetic field. And of course, the direction of the magnetic field. That creates then either a force, or which is then an electric motor, or we go the other way around, and that is then a generator, meaning we generate electricity, which means we push electrons into a certain direction through a wire, for example. So we'll cover that in more detail later on, but that's already covering a couple of things. So electrons must flow, and they flow because there's a force, which is squeezing them, pushing them, pulling them, whatever, through that wire. They cannot escape the wire. It's kind of logic, yet still, theoretically, they could jump out of the wire, which they don't. So they are kept inside the wire, and henceforth, because there's a force, they are pushed forward. Without that force, they are not moving. That's extremely important to remember, although it seems quite obvious, of course, but that they will only flow when there's a force. We'll come to that, why it's like that. And when we look at it, we know that from, well, previous levels of physics we did. Of course, the electrons are free in the metal, huh? And henceforth, if there's a force applied, they can accordingly float. So actually, we talk about an ionized situation in a metal, even from the outside. It's not charged. It's neutral, as long as there's no power flowing, of course, no potential difference, no force. So just a wire, metal wire. Of course, you can touch it. It will not give you an electric bolt or anything, but the basic structure is as such that there's the core, the nuclei, positively charged, and the electrons are freely moving, negatively charged, but they're in balance. So they are not any, even if you go into huge numbers, there's not one electron missing, so to speak, in terms of where it belongs to, in terms of making it electrically balanced, uncharged to the outside. So that's one part. And we know that they will flow along the wire, of course. And something interesting as well is when you plug in the wire, as a plug in the cable, you have a consumer, a light bulb, for example. Will that, the moment you switch it on, will the light go on instantly, or will it take a while? We talk human timing, huh? Not, so just everyday life timing.
Oh, instantly.
So when you switch it on,
Instantly.
yeah, instantly. Sorry, yeah, exactly, right. So instantly. So now, does that mean that the electrons travel so fast from the exit of the socket, or what do you think happens?
The whole current moves. So.
Yeah, right. So you can say basically, if that's the start, so there's the socket. The moment we close the circuit, that means they start to nudge each other, right? So the first one here, poof, drops out of the wire, so to speak, meaning goes into the lamp, for example. But they still float, huh? So there's kind of a double effect. On one side, the potential difference makes them nudge the next one, so instantly we have what we see as power available, or in that case, light goes on. And on the other hand, they still drift. Or that's what we call the drift speed, or the velocity. We could cover that today as well. Or what speed actually do the electrons travel? So they travel. They really move. They're not static. The first instant is they nudge. So hence the first one goes on. Light goes on. But then there is a flow. There's a true flow of these electrons. So it's a physical movement, actually, of these electrons. It's important to remember. Which is a bit more obvious, of course, if we are in an electrolyte. That means we have the negative and the positive ions. So obviously, the negative ions would be the electrons. The positive ones would just be positively charged particles. That could be an element, that could be a molecule, whatever. So there's the electrolysis is obviously a practical application of that. We will cover that later on as well. And that could be something like that. And of course here they flow much easier instead of in a wire, like here, for example. So that's why this is just another showing very clearly, very easily, that of course the plus charges go away from the plus poles and the minus charges go away from the minus. So actually they will settle down, so to speak, on that one. And the positive ones will settle down on this one. And then we have terms for that, cathode, anode, etc. But just at this moment, just to give an idea of the flow of these particles. Now, just add one more page. So now that we talk about current, we talk about these electrons moving, so we can give a simple definition, say, well, the current is actually nothing else but a charge, because an electron, for example, let's focus on that one, is a charge over time. This is the most simple definition of a charge. And of course, we can reverse that and then say a charge is hence worth nothing else but current times time. Current times time. So if we talk about a certain flow multiplied by the time, we get the individual charges, the number of charges, for example, or if we measure it in a different dimension, maybe in energy or whatever, we can then say how much energy has flown. Or better focused now in when we say charge. So there's one way now we can say as well, coming back to our more mathematical definition or writing, we can say so that increment or that part of charges is actually the current times time. The one I like more, frankly speaking, is this one. Current is charge over time, because that makes mathematically more, to my opinion, more sense to memorize it, because it's a very typical pattern. We say the change, the delta, the change of current, or the amount of current, the amount of charge over a certain amount of time. So that is the current. So of course, quite often we see it like this, but of course we can always rearrange it. So this one is more memorable, I think, just to say, well, current over time. That's, how do I say that? Charge over time is the current.
Yeah.
So this is having quite a big impact then on the fundamentals, coming from a simple observation to more complicated, calculations actually. And just going to this one now, making a brief small question. If you can just look at not number one, sorry, we look at this one first. And when we look at that, what is now the direction of the conventional current in that drawing? How do I have to draw the conventional current in that situation?
Like anti-clockwise.
Yeah, exactly. So for plus to minus, so it will flow something like here, huh?
Yeah.
Agree?
Yeah.
Okay, exactly. So that's, and we see, and here it's very obvious, and that's quite nice actually. Here we see very clearly, well, but the electrons, they flow exactly in the opposite direction, right?
Oh.
If we would have agreed in the past that the conventional current is, or let's say we would have named the electrons positive for whatever reason, and we would have called what we call nowadays protons usually, or positively charged particles. If you would have called them electrons at that time, we would have had no problem to have two separate directions of the electric current flow. So this one is quite nicely actually showing. So I used the green one. So actually, that was not the idea. So That is the electron flow. Huh? This is the flow, and we see that very clearly. They flow, of course, away from minus towards the plus. This is the basic concept, plus and minus. And of course, the pluses go to the minus side. That is equivalent to the conventional current. So when we usually talk about the current, then we talk about the conventional current, which means plus to minus. Okay, good. And now we go to this one. So now we have to draw the cell, huh? How do we now indicate? So this is very important because when we draw a circuit, we go by the conventional current. And henceforth, now we have to make the circuit complete because here it's only showing A and B, but no indication of the cell and its charges, so to speak, or what is the positive end and what is the negative end. Huh? So when you look at this one now, where do I have to make the positive end, in A or in B?
B.
Exactly, huh? All right. So make it here, or actually combined. So I should make it away from it, so like that, huh? And hence like this, huh? And there we go again. So even if I do not write now plus and minus, the longer one is always the plus, right? Like we said before, this is the minus. So I don't have to write that, or you may get a circuit actually, which is exactly looking like that, like what we just did. Could look like that without any further. Then we know exactly that's from plus to minus. So whatever is then happening, I have to keep that in mind of what I'm talking about. But if there would be a question related to the electron flow, of course, I know exactly it's the opposite. So this is a very typical picture then you would get without the further indication of plus and minus. Huh? Okay. So now we have to indicate. Shift that a bit. Okay, make it again. Okay, now to indicate the flow, like in question B, what is now the direction of the conventional current in the solution?
Clockwise.
Yeah, exactly. Huh? So we can say this is the conventional current. Huh? Exactly. All right. And in the connecting wires?
It's still like.
It's a trick. Yeah, exactly. Right? It's nearly a trick question, actually. Of course, there's no change, but people sometimes, if not completely understanding that basic principle, they may suddenly think, no, but it's electrons flowing. So yes, of course, the plus, and that is of course flowing in this direction. And then they think, but wait, it's in the wire, it's the electron, so henceforth it must be the opposite. That would be, of course, correct, but it's not the question. The question is about the direction of the conventional current. So, of course, in that sense, like we drew it before, the current goes all the way, because otherwise they would collide. I mean, that's impossible, physically speaking. Huh?
Yeah.
Okay, all right. So we have discussed now these charges over time, and having done that, let's continue. I have a couple more questions now. Sorry, we can do them here actually. So, question 3, we say the current in a circuit is 0.4 amps. So what we have not covered is the dimensioning. So when we talk about current, obviously the unit of measurement is amps, which means in proper expression, proper wording, Chris, what is amps? What is the the real scientific name.
Ampere.
Ampere, exactly. So, and obviously amperes reflects nothing else but the charge over time. So do you know the unit of measurement for the charge? For Q?
The coulomb.
Yeah, very good, exactly. So this is Coulomb per second, huh? So, or in other words, Coulomb per second, which is amps, ampere, like this. Bless you. Okay, so we have Monsieur Ampere, obviously, and Monsieur Coulomb. Huh? They were the ones. So Coulomb is the one who says, okay, there's a charge. We come to the value of that in more detail, and if that's flowing, of course, then we have a current, which we then call ampere, because of Monsieur Ampere worked more with those currents than in consequence. Okay, so we have that current now of 0.4 amps, and we have a time period of 15 seconds. So of course we want to know how many, or what is the amount of charges which has passed in that time.
0.4 times 50.
Okay, exactly, yep. And that would be how much?
6.
6, huh? And in terms of measurement, Hainsworth?
Coulomb.
Coulomb, exactly, huh? So there we go. So this is a bit where we have the change of measurement units, right? A bit different. Let's say when we are used to say force is a Newton, for example, and it's a result of other measurements, SI units actually. Here it's a bit different. So the charge, yes, of course, we could is then just a Coulomb, right? So that is then the result of time or seconds times ampere, if you want to say so. Okay. Or to be like what we did, we came from the idea of I is delta Q over delta T, huh? So that was just a rearrangement we did. So that's obviously very helpful to keep that in mind as a base formula. Now going the other way around, and when we say, okay, we have 150 coulombs as a charge which has flown during 30 seconds. So we said, what is the current in consequence of that?
150 divided by 30.
Yeah, exactly. So in that is then how much?
5 ampere.
Yeah, exactly. Yeah. So the reason why they chose those numbers, of course, is just to give us a bit an idea of typical household fuse. That could be 5 amps. So which is then obviously the amps. When we talk about ampere, about how much current, joules, whatever electricity we can get from our power grid. We quite often do not talk about the power. We just talk about the current, which is kind of a bit imprecise to some degree. But nevertheless, when you say 5 amps, that means you could get the amount, or when you say 5 amps, that means coulombs per second, right? So what does that mean in other words, if we translate it into another wording? What are these 5 amps?
5 coulombs per second.
Exactly, huh? So that would be, so that is then quite helpful to remember that we say, okay, that's how many charges or how much charge, it depends on how you look at it, just as a flow or as various electrons coming out of it. You can say how much charge I can get within a second. And obviously we always measure everything per second usually. So that's giving me then an idea of how much energy ultimately I can get, huh? Or as a first step, the charge. Huh? We don't know yet if that's a lot or not. That is something we have to figure out in due time as well. And then another one, of course, same thing. If you have 50, that's useless. I'll leave that question. That's the same thing, just with the different values. But this one is now an interesting one. This is a bit like what we discussed before. And it says a battery, 50 amp hours. Label on a car battery, for example, or any battery, doesn't matter. But it needs to be a bit more powerful one. So it says 50 amp hours. What does that mean, first of all? In its most simple terms, just that, what you can read here. What does that tell you in explicit words?
Is it the amount of charge?
Yes and yeah, that's a good one, but that's the consequence of it. When you just look at the face value, what you see here.
50 amps every hour.
Yeah, yeah, exactly, right. So it's very straightforward, actually. So it's a very practical term, which we, physically speaking, it's like, sorry, you should use different units, dear manufacturer, but this is how the common practical application works, and it makes a lot of sense that I say, oh, okay, I get 50 amps for 1 hour, right? That's what it says. Very simple, straightforward. I may, of course, use 100 amps in 2 hours, so 50 in 2 hours. So then I use, of course, 25 per hour, etc. But that is the maximum I can get. That's what it means, 50 amps for 1 hour. And now, of course, comes the question. It depends on the consumer. Of course, if I have a consumer which needs exactly 50 amps, I can, of course, exactly run it for 1 hour. That's exactly what we see with the cars, the electric vehicles, right? Of course, there we rather talk about distance than time, but in that context, we talk about time. So if I now have a consumer for 200 amps, how long can I drive, for example? Yeah, that's question 6. Doesn't matter. But... So how long can you drive when you have a consumer which uses or needs 200 amps, or you push the pedal, so to speak, in the car, that you go rather fast, which obviously needs more, amps, more energy, current. How long can you drive when you continuously use, when you use 200 amps?
15 minutes.
With that battery? Yeah, exactly. And why?
Because you're using the current 4 times more.
Yeah, exactly. Yeah, exactly. So I use my, this is 4 times the 50 amps, and T is 1 quarter, which means obviously 15 minutes then. Exactly. It's a very straightforward logic connection, right? Between how much you have at your disposal and for how do you let it run, or how much do you utilize from what you have at your availability. Henceforth, of course, you can only use it for a reduced number of time. And when we go to question B and say, okay, what charge was flowing in that time? What amount of charge it was flowing? What is my Q or delta Q?
50,
for that whole
50 times 60 times 60.
Yeah, very good. Exactly right. So say it again, please.
50 times 60 times 60.
Ah, okay. I know I say, but I still ask, why do you say 50? When you look at what we did in example A, huh? So make sure we use the 200 amps.
Yeah.
The supply is 50 amps for 1 hour, but currently I'm using 200 amps because I can. Yes, the system has a bit to be designed that it can really push through 200 amps. That's a dimensioning question of the wires, but obviously assuming it's possible, I'm using 200 amps now, which is obviously more. Let's say the other one is just an energy reservoir, kind of, right? It's what it has stored, and then as long as the system allows me, I can even use 1000 amps, of course, assuming the wires are dimensioned for that, or I can use, of course, 10 amps. Depends on, and that's why an electric car is quite a good example, actually, because it may vary depending on how fast you drive, of how much current you need at that very moment, actually. So now we go back to example A, so 200 amps. So henceforth, what is my calculation? You were quite right, Chris, but something was not numeric-wise not correct in terms of that I'm using 200 amps.
200 times 15 times 60.
Yeah, exactly. Huh? Exactly. So what we have is nothing else but our current, the one I'm using, which is 200, over my times my delta t. Huh? So that was in this case 200, and my delta t was 15 minutes, which I calculated here. Huh? That is this one. Then, of course, I have to make it into the right unit of measurement, because we're talking about coulombs per second, huh? Or coulombs then in the end. And that is how much?
180,000.
Exactly. Huh? And what?
Coulombs.
Coulombs, exactly. Huh? That's important to get a bit familiarized with that one. So whenever we talk about Q or delta Q, we talk about coulombs, which is nothing else but a certain electric charge, right? So we don't know yet what that really means. We'll look into that. And even if we know it, it's probably something a bit untouchable, a bit difficult to imagine. But obviously, it has to do with the amount of electrons somehow, which are at our disposal in order to get that charge, right? So we need to have a number of electrons in the end to get that charge. And because we know from chemistry that the charge of an electron is the same as the charge of a proton, that's quite fascinating, because we know that the electron is much, much smaller, or less in weight, and smaller henceforth as well, than the proton, and yet they have the same charge. So that makes somehow a fascinating observation. Seems very logic when we look at it. But if you think about it, that you have a particle which is, one is the size 10 to the power of minus 27, and the other one is also the mass, and the other one is 10 to the power of minus 31. So there's a difference of 10 to the power of 4 in between, or minus 4, which means that as ultimately, if a smaller particle, as we know as well, when it comes to size, the same thing. So it's much, much higher in density, right, of an electric charge compared to the proton. And that makes it very interesting. That's why the original experiments were always with electrons. Only nowadays, well, maybe for the last 20 years plus, 25 years, they use protons as well in these physical experiments. In these colliders, right? There's, if you ever have a chance and you're interested, Chris, then I highly recommend. There's several ones, but one of the largest ones is actually in Geneva, in Switzerland. That's a collider. It is a ring system, like a donut, which is 25 kilometers in diameter. So it's underground, partially in Switzerland, partially in France. And that's with a very demanding system you can imagine you have to have magnets, you have to have evacuated tubes and all, where they accelerate electrons originally, nowadays protons, and try to accelerate them nearly to the speed of light. So that needs a massive amount of energy just to accelerate one particle actually, and then smash it into each other and see what happens. And that's how they found actually more components, so beyond the electrons. Not so long ago, it was thought that protons and electrons are the end of the line, but in the meantime, we know they consist again of further Lego particles, so to speak. So an electron is made of other parts, etc. So just to get a bit an idea of the relationship between these electrons, protons, charges, currents, and all that stuff. Okay. And now I would like to go into that charge. We'll come to that afterwards. So we talked so much about charge, and electrons. The charge of an electron is approximately no, not the Q. Sorry, the Q of an electron is about minus, because it's minus charge, minus 1.6 times 10 to the power of minus 19 coulombs. So this is a number. You will remember that by heart, because it always comes again and again when you later on move on to nuclear physics and stuff like that. Then we always deal with these or electron volts actually come into play then at some point. So this is the charge. So one electron has such a tiny little charge. So now the question is, how do we get 1 coulomb, right? So we talk about 1 coulomb. So we need, I just write it for the fun of it. So 6 X. I have to make sure I'm not. One missing. Okay. Put it a bit to the front. Okay, here we go. So this is how many, the number of electrons we need. So the number of electrons. So this is 6, okay, it nearly doesn't matter anymore. Then 1, 2, 3, 4, 5, 6 packs of to the power of 3. So that's how many electrons we need. Then we have 1 electron, 1 coulomb of a charge. And this is important because it's really a physical situation. It's not just coming out of the blue, just, oh yeah, we have a charge. It really means that we amass this amount of, in other words, 6 times 10 to the power of 18 number of electrons and electrons in order to get 1 coulomb. And which means, of course, now if you just go back to what I said, that the difference is in terms of mass is minus 27 to minus 38, 31. This is the proton, and this is the electron, the mass. So you can see, well, if I need to say for the same charge, which there is a coulomb, I mean, ultimately I have a plus charge as well, especially when I start to split. And if I have then, like in our electrolyte, the positive charges and the negative charges, they must be equivalent. So that means if I would manage to have the protons and the electrons in whatever way, not just already a molecule, but an individual proton, then I would have, of course, a very different mass because of that difference here between masses, right? So 10 to the power of 4. So whatever weight the electrons are, the protons would weigh 10 to the power of 4 more. So that could become quite an issue. And of course, you can imagine that 10 to the power of 4 is exactly the reason why we started with, or physicians started with electrons for these collision experiments, because of course mass means force, means we need much less force in order to accelerate an electron compared to a proton, right? That's as simple as that in the end. So that's all, everything connected. And I would like to do the following, making this a bit more, just to get the charge once more. I think we have, let me see. Yeah, let's go the other way around. Just as one simple example, we have a current of 10 amps, 10 ampere. 10 ampere, we have it, we leave it for 1 hour. And of course, we want to know the charge flow, huh? Once more. So how do I calculate that?
Ten times 60 times 60.
Yeah. Or our famous 3,600 seconds, right? Exactly. So we can as well say 10 times 1,600. So obviously 36,000. Huh? Okay, so easy, right? So charge flow, it's more in the word that we are not getting confused. Sometimes they calculate the charge, sometimes it's written calculate the charge flow. So basically, and you see in the delta Q, there's actually the flow included kind of with the delta, the differential, right? Which means there's a change of charge, which means, in other words, there's a flow of the charge. Even if it's not the flow per se, that's then the current ultimately. So it needs the time element, but at least something, the amount of which has been moved within 1 second ultimately, that's in our current. Huh? Okay. And just to do as a very simple side remark, if we would have to call the electric, calculate the charge, that we let me put it like that. So that's something else like this. So if I'm telling you the charge has been 3.2 times 10 to the power of minus 19 coulomb, and I'm telling you 2.5 times 10 to the power of minus 19. This is 1, this is 2. One of the two, which one of the two current is possible, physically possible? Because one is not possible. So one is physically an impossible current flow. I mean, an impossible charge flow or charge.
Oh, number 2.
Yeah, and why?
Because you cannot, like, because there's one electron and then also one incomplete electron.
Yeah, exactly, right. So that's why the 1.6, right, is really kind of a magic number in that regards. Then we can only have integer multiples, of course, of that one. Like you say, it has to be a full electron. Of course, in particle physics, you could start to argue and say, no, I have quarks and that, whatever else, but we are not there. We're just dealing with kind of simple, straightforward electric issues here. Exactly. Huh? Important to keep in mind, because hopefully there's never any question in any physics tests which is leading to something like that. Then, because the first assumption would be, I did a wrong calculation. It can't be, it must be a multiple integer. But you never know, sometimes it may be that by kind of mistake, the resulting charge flow is actually physically not possible, but it's still the proper calculation. That would not be ideal, but sometimes it happens. But at first, just check, can it be divided by 1.6? Then you are certainly right. If it's not, cross-check. If you still come back with the same result, obviously the question was a bit not so ideally formulated. Huh? All right. Now, the next one we want to deal with, of course, is, okay, we talk so much about current, we talk about charges, and now we can combine, of course, everything together once more with the basic dimensioning. And you see actually here, this is, well, the basic dimensioning in order to achieve a certain current in the end. Assuming that the charges flow through a wire, which is the normal situation actually. Even if it's in a so-called printed electronic circuit, it's still kind of a wire dimension, a very tiny little level. And you see we talk about the length as an impact. Of course, the number of electrons have an impact. And of course, how much can flow through the section area. So in other words, and we typically in that context call then the individual charges, we call them small cap Q. So to make it a bit more general. So we could call it electron flow or proton flow, but in general terms, it's the individual charge which is resulting then in the big Q. That's the number of all these small charges together having been transported within an amount of time. And obviously, it depends then on how many of these particles, these charged particles can be even around in a certain dimension, so to speak. And when we look at that, let's start with the number of electrons. So how many electrons could there be, Chris? Just starting with that one. How many electrons, when you look at that dimension, how would you say how many electrons can there be in that wire section? So we talk about this one is part of the dimension, and then of course the length. So that's that cylinder, so to speak. How many electrons can that cylinder contain? Or will it contain? How do I put that formula together?
Like the cross-sectional area times the length.
Yeah, okay, that's a good one. So we have the volume, right? Yep. Okay. And times what? We know that actually from the last chapter, kind of. I mean, we know it anyway, ultimately, but last chapter we focused a lot on that in chapter 7. What was a one which we always looked at in the last chapter, Chris?
Like density?
Yeah, density, exactly. So now I have to correct a bit what I wrote here. Let's just call that the number, So and this one is the density number. So in electricity or here we use the N. Of course, we could use the density number symbol, but we don't. So N is representing not the number of electrons, but the density. So how many electrons per whatever, per volume, obviously. So in other words, N is actually number of electrons per volume, so to speak. Just to keep that in mind. And not just the absolute number. The absolute number is then, well, something else. Well, what I used here with the typical counter symbol. But that's, of course, just shorthand for number of electrons. I don't want to write it. Save some ink. So, okay, that's one part. And now the charge of the electrons. And charge of the electrons, how do we get them?
Number of electrons times the, I think 6 times 10 to the power. I forgot.
Yeah, that's fine. Yeah, what you mean is the electron charge, huh? Okay, yeah. So times the charge of the electron, huh? Exactly, which is very obvious, right? I mean, we have a charge per electron, and we multiply that with the number of electrons. Of course, that's a total charge. Exactly. So actually it's quite straightforward. So of course we utilize what we already had defined. So N times A times L, volume times the density. And now we multiply that with the charge of an electron. And which means then now to figure out the current, actually, we can say, okay, now I want to know the current, because that's what I'm interested in. So the current is, of course, my I. And what is now the current? When you just in its most simple definition, which we already encountered, because it's still the same, there's nothing changed.
Coulomb per second.
Yeah, exactly. So that means, and as we have the charge, which is this one, actually this is Q of the electron, right? So we can introduce that one, say, okay, now I just make the delta Q over delta T. So I can just write still N times A times L, because that's my Q. And I do my electron over T. I could do that for any, but this is easier. You will see why this is the better way to write it down like that. And when I now substitute, now, well, okay, no, let's do it the other. I make something else, which is more easy to see. Times electron times, well, okay, I do it in 2 steps. Sorry for my. So I say L, of course, times charge over time. So I keep that delta Q in mind, so to speak, with this one, what I do first, because it's charge. But we had already said this is part of it. So now I just say charge per time. And now comes a typical kind of mathematical trick. And I say, wait a minute, if I rearrange that, and I do this one, I do length over time. What is length over time, Chris? What do you think? Or in general terms, what is length over time?
Speed.
Yeah, exactly, right? And that's the whole idea here, actually. So that rearrangement leads me to the situation where I can say this one times A, and now comes the point, times speed times the individual times the charge. So still like this, huh? That makes now something very interesting. Or of course I can generalize that, like I said before. I can as well say this is N times A times V times Q, by generalizing the charge into Q instead of specific an electron. So it would be true for any charged particle, actually. Is that okay so far?
Yeah.
So we can very nicely say this is the current, and this is in these regards, it's depending on the diameter. Well, basically the diameter of my wire. Of course, it depends on the N times E, how many electrons are flowing. So this is the density times the charge of the electron. So if I have a higher dense material, of course, it's a different number of electrons I get compared to one with a lower density. It's very important to remember that. And it depends on the speed as well, of course. So the speed is obviously not light speed. It's, well, probably depending on how fast it can really flow. This is something we have to figure out. And what we can, just to close it here actually as well, is to say, well, this is just, this is the general formula usually. So we keep in mind when we talk about that. So, I mean, I just have to quickly check That went missing. Let me see. Because I wanted to discuss this one now. First, let's make a calculation, and then we can look at the various flow principles. Okay. Let me just have a. That's the one. So we will come to that, but that gives you an idea that if you have, for example, a material, this one, but you make it into a different dimension at some point, it will have its impact on the speed. Of course, looking at the formula, we can instantly say what will happen. Or it can be a different material which has a very much lower density, you see, less electrons per volume compared to this one. That has its impact as well. So this is something we're going to look at after we've done a couple of examples. And going back to our dimensioning. So what we want to calculate now is the what we call that the drift velocity usually. So the drift velocity. Quite often we just talk about the velocity of the electron, but because they really travel very slow actually in the wire, it's like drifting, which means slow movement, right? And that's why from a very practical everyday language we use that as well. So we talk about the copper wire. We talk about an area of 5 times 10 to the minus 6. So very small, no square meter, excuse me. We make life a bit easier. And that's cross section, so we have to make sure we are. And then we have a current of a 1 amp there. And the electron density is 8.5 times 10 to the power of 28 per cubic meter. So that is actually a real value. It is 10 to the power of 28. And we cover that briefly then in the next discussion, if there's material with a different type of density. So what we want to know is now that drift velocity. So how do I calculate the drift velocity, Chris? You can just first tell me the basic formula, then the rearrangement, and then we go into the values. That's usually the best approach. So what is the basic formula now you will use for that calculation of that drift velocity?
Like length over time.
Yes and no. I mean, when you look at here, I mean, actually this one, right?
Yeah.
So in order to calculate, you have to take into consideration all the factors. You have to take into consideration the volume, but we don't, which would be here, actually. But in my example, I'm not giving any length, but for good reason in that context, because I don't need it, because this is just the application of this basic formula where I actually replaced my length with velocity, which helps me on the other hand then to calculate the velocity. Of course, I could then go one step further and say, well, imagine that was for 10 seconds. Of course, I could even calculate the length of the wire, but that's not the question here. Huh? So coming from the side of, well, I need the density of how many electrons about the diameter. That's the core dimensioning factor in that context, times the velocity times the charge of the electron, or Q. I mean, this is, I could as well write the charge of the electron like that. Same thing. Now, if I check now, of course, and I want to know, obviously, the drift velocity. Huh? So you can see that from that current, because it's a physical flow of electrons, and it's a question of how many of these electrons in total flow through the cross section. That's what it is. It's like a flow of water, actually. Same thing. How much water is flowing in a pipe? When you have a cross section of the pipe of so much, and you know the flow speed of the water, then same thing. So there's the one-on-one link between, say, water flow and electron or charged particle flow. So how does the rearranged formula look like, Chris?
I over n
Yo.
times a times the electron charge.
Yeah, exactly. Huh? All right. So, and as we have all the values, we have the 1 amp. So that makes everything easy. It's just the reverse, actually. N, we have our 8.5 times 10 to the power of 28. We have our cross section, which is 5 times 10 to the power of minus 6. So I can as well take it up. I see some simplifications. And of course, I have to have the charge. Huh? So that is something which you can check in the formula booklet, for example. So this is, but again, over time, you will remember, it's over 1.6 times 10 to the power of minus 19. Huh? So I write it a bit in a better form because otherwise it looks like over 8.5 times 10 to the power of 28 times 5 to the power of minus 26 times 1.6 to the power of 10 to minus 19. Huh? Yeah, that should be a minus 19. Okay, so have you calculated it, Chris, eventually? Otherwise, I just give you the number.
No, it's too long.
Okay, okay, that's fine. Okay, so what it will result in is 1.47 times 10 to the minus 5 meter per second. So that will not tell us so much yet. So if I translate that into more tangible numbers for myself, so to speak, not in physical terms, of course, then it's really slow because it's, which of course makes on the other hand sense that we say one electron is really tiny. So comparatively to the size of the electron, it still has a certain velocity, right? Because it's really small. So it's not 1 millimeter, it's not 0.1 millimeter, it's 0.01 millimeter. So it's still kind of observable, so to speak, with the human eye. When you look at a ruler, somehow you could see that if it's really finely made, high precision, for example. Then you could say, wow, so that electron, that tiny little fellow, is actually within 1 second moving within that distance. And given the fact that we clearly cannot see the electrons and it travels that big distance, so now of course we could say how big is an electron? So yeah, then we would see, wow, that's actually quite a distance it travels within that time. But from our perspective of the human sizing, of course, it's like nothing. But for the electron, it's huge. Huh? So that's why we, on the other hand, we can clearly explain, hey, if the electron is only traveling with 0.01 millimeter per second, of course, no way it can travel through the length of a wire of, say, 2 meters, and we get instant light. So that cannot be the reason, right? And we know it's just because it's densely packed with these electrons. So the moment I have this potential difference, I plug it in, I have a force, a pressure. So of course they start to nudge each other, and hence the electron is, well, lighting up the light bulb, for example, or stuff. Okay. So that is something interesting to realize. And let me just see. No, we don't do that right now. So I would like to do this one. Move it a bit down, because what we can say now is we have rearranged our equation. So I will write it down once more, and we could say going back to replacing the so we could say it's current, and of course, like what we had before, N times A times E. Huh? This is the one. So that means now we can conclude from that basically three conclusions. The first one is we can say, well, the velocity is proportional to the current. Very clear, right? The higher the current, the higher the velocity. I can say velocity as well is proportional to I just want to cross check. This is a bit Okay, you may say so. If the relationship between the this is not so obvious. Let's do this one first. The other one needs a bit more explanation. So that we can say, well, it's equivalent to 1 over n, for example, right? This is another conclusion I can say on a separate statement when I look at it and say, well, the higher the number or the higher the density, the less the flow, or in other words, the lower the density, the higher the drift velocity, which makes very practical sense, because if I imagine that there's only a few electrons, of course, they're free to move. So that means they can obviously, under just general considerations, flow faster because there's less hindrances in the way in order to move forward. They don't bump into each other, so to speak, if there's less. So that means it's, or in other words, it's inverse proportional to the density, right? So the higher the density, the less the velocity. So we can as well put it like that. Excuse me. N minus 1. That's sometimes a bit more clear to our understanding. It's just the inverse relationship. And number 3, this is a bit more. We just look at, say, I over A as a separate issue, for example. And because the charges are the same, so that doesn't matter. It can be an electron or a proton, same charge. Because we talk a single individual particle charge, not the sum of it. That's why the E has no impact. That could be a trick question when it says, well, imagine you replace the electron flow with the proton flow. How will the velocity, the drift velocity, be influenced? Of course, the answer is it will be not. It won't be, because both the electron and the proton have the same charge as a particle. Hence, it's only the flow direction which will change. But if that's not the question, then it's just, well, same. But if it's just in general terms, how will it influence that? Then some will probably say, well, it may travel in a different velocity. No, it will not. But it will change its direction of the flow, because it's then from minus to plus. Huh? Also changing the direction flow. Okay, and this one, the last one, is then if you have I over A, that means how much current is in a wire. So if the relationship changes, for example, which is depending on the diameter, actually. So we could as well say proportional to the A, but current has an impact. So under the assumption of the same current, by modifying the diameter, making it slimmer or making it wider, then of course the velocity will change. So that's why we list the I here as well, because we cannot just say the velocity is 1 over A. That is not the relationship we want to emphasize here. It has to be in relation to the current flowing, but under the assumption of the same current, of course, then the geometry, the diameter makes a big impact. Huh? So that means, in other words, if I have a thinner wire, they will flow faster. And this is exactly then an explanation why a thin wire may start to heat up, because the fast flow of the electrons is leading to more frictions, because there's a certain density. They bump more into each other, but they cannot escape because it's a small wire. and henceforth it starts to heat up faster because it's a thin wire. If I have a thick wire, there may be hardly any heating up of that because they are not compressed now with the change of velocity. Huh? So that's the point. And that is illustrated here in simple terms. So if I increase the current, so of course I increase the speed. Huh? And you can see here, this is the classical, traditional, conventional current flow. That's why the arrow goes in that direction. But as I look at the electrons flowing, of course, they flow in a different direction. Now, that's important to keep in mind always. When you would have to give an explanation and you make a drawing and you say, well, the current, which then is, of course, the classic conventional current, because that's what you talk about usually from the outside, is like this. But the electrons, of course, still flow in that direction. Huh? So that means if I double the current, I double the speed. This is exactly this one, proportional. And if I now reduce the diameter by half, or the area actually, should be careful, not the diameter, the area is half the area. Of course, I have to double the speed. This is because it's proportional. It's in a linear relationship. Double, 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 half. Huh? So this is what it says here because it's inverse proportional. And last but not least, of course, if I have less electrons in it, well, of course, then the speed has to increase because I have a certain current to achieve. So they must increase their velocity in order to generate the same current. Is that the last one? Is that one clear?
Yeah.
Please.
Yeah.
Okay. All right. Good. Then, okay, we've come to the end for today. So we will just continue next time. Is that okay? With the same subject and answer more questions?
Yeah. It's okay.
All right. Okay. Then we have standard. Next time is Friday again. So hopefully you are feeling better. Good recovery. And see you next Friday. Huh?
Yeah. The ending this stream.